So hello my dear students. So here we are going to study a new chapter, class 12 chapter 1, relation and function, and this is going to be a very interesting chapter, and I hope you have gone through it very nicely in class 11's topic. So in the class 11 you already got two consecutive chapter, one is set, one is relation functions. If that is clear, then obviously this topic will be very crystal clear to you. So let us have a quick revision of our class 11 concept. What does the actual relation means? Relations are from a non-empty set A, from an empty set A to the non-empty set B. B is a subset of the Cartesian product A cross B. So whatever the Cartesian product you get means ordered pair of A cross B. Let us consider an element having in A set is A, B, C, and the element present in the B are P, Q, R, S, or you can consider a numerical value for that. Let us consider a numerical value 1, 2, 3, 4. So if you want to make a relation, let us use a ray diagram for more better understanding. So if you use a ray diagram, so A related to B or A related to 1. Also you can see B is related to 2, C is related to 3. Yeah, this is a perfect relation. So this is a relation. So this is a perfect relation here. Means it is the shortcut form. What we can say that subset of the Cartesian product of A cross B. Subset of the Cartesian product A cross B. Anyway, how can you, your wish, any way you can arrange. And remember, already I told you, the set of first means element of the first set is called set of domain, and the set of means the element of second set is called set of codomain. Alright, and those number or those values which are occupied or which is the image of the particular domain are called the range. I already told you. So you can go, there is numerous example you can carry on. You can formulate your own ray diagram also for better understanding. You can very easy. Suppose let us consider A, B. If you want to set a relation, suppose let us consider a relation. Suppose set A is a mark scored, whatever. It's a mark scored. Yeah, for name of the students you consider, suppose A, B, C, D. These are the candidate names. And suppose B is a set of marks scored in mathematics. Let us consider 1, 2, 3, 4, 5, 6, whatever. So if I say suppose A got 2, B got 1, C got 3, D got 4, C got 5. So this is a relation. Means this is an ordered pair of A cross B is called a relation. Not a big deal. It's a simple case. I hope the statement is clear. It is not have to be discussed in class 12, but for better understanding, I just recall you up what does a relation means. So then we're going to study about the types of relation that is given in the chapter, and then we'll go on function, definition of function, type of functions, and then combination of function, GOF, composite function. These are things that we're going to study in the chapter. Stay tuned. So let us go now to the type of relations. So here are the following types of relations that we are going to study. The first is your empty relations, next is your universal relation, third is your reflexive relation, fourth is your symmetric relation, and fifth is your transitive relations. And for better understanding, let me explain each and every terms, what does it actually means with proper definition. So here goes the first type of relation, that is empty relation. Definition goes here. A relation R in a set A is called empty relation if no element of A is related to any element of B. That means suppose there is an element A, means there is one set A and there is another set. Consider same sets, come on, A, both are same set. Let us consider both are as a same set, and there are lots of elements are there. Suppose A, B, C. Here also A, B, C. But not a single element of A is related to any of the element of that another set. Means not a single element of domain is related to any of the element of the codomain. Simple. That means what? That is what we can write. The relation is phi. There is no more element is present in this relation. This phi is belong to A cross A, and this is the simple definition. for the empty relation. I hope it is clear. It is not so important. Just the matter of fact is that you need to understand it very well, so that it may come into various application to understand the question better way. Now let us go to the next definition, that is universal relation. Nice relation. A relation R in a set A is called a universal relation if each element of A is related to every element of A. There is two different set of A cross A. Suppose this is a set A, this another set, same set A. So this is A, this is another set A. Let us consider the element presence are A, B, C, D. Here also consider A, B, C, D. So we consider it. So it is according to the definition, it is said that each and every element is related to the set of codomain. It is called universal relation. I hope you can catch what I am saying. It's very simple. Suppose let us consider A, D, D, D. You can see all are related. Okay. So you can I can also write like that also. I can also write this one like that also, like that related. This one also. So B is B, C, D. Means whatever, how you make the ordered pair, your possible way, it is your way. So you are going to get what? The universal relation. Means each and every element, just point to be noted. It is said that a relation R in a set A is called the universal relation if each element of set A, if each element of the set A is related to every element of set another A. That is, the relation is totally equal to A cross A. Means whatever the number of ordered pair you will be getting in A cross A, that is called your universal relation. I hope you can catch what I mean to say. Now, thing is that now both there's a point, remember, not both these empty and universal relation, sometimes called relation, sometime called trivial relation. Just remember it, it's a very nice topic. Means these empty relations or the universal relation are there sometimes defined as, or it is denoted by the term trivial relation. It's an important thing to be noted. So for better understanding the empty set and the universal set, let me describe with an example, a very beautiful example. So consider there is a relation between the set A to A, and the set A is a set of all boys. Set A is a set of all boys, of a class, set of all boys of a class. If I consider a relation like that, a relation is defined like that. Relation R is defined like that, such that A comma B, where A is the sister of B. Now tell me, what are the elements present in this relation? I already mentioned that A is a set of all boys. How come the sister here? There is no any female gender present here. That means if you do the relation between across the two set, that is set A and another set A, where the set A is also boys and another set A is also boys. So how the boys can be sisters of each other? So that means the relation is pi. There's no more elements are present in this relation. I hope it is clear, everyone. Now, for understanding this universal relation, let me use the same example. If I say now, the relation is defined such a way. The relation is defined such a that A cross B, and the difference of A, the difference of A means the height difference. The difference of A and B is 3 meter. or is less than 3 meter, is less than 3 meter, less than, I hope it is clear. Means if I subtract the height of the individual candidate of the class, and I will be definitely obtaining less than 3 meter only. So have you seen any person which is more than 3 meter? So obviously when you subtract, means when you subtract the height of any two individual, it will be definitely less than 3 meter. That is sure, compulsory, certain. That is why we can say that this relation is universal. Means whatever relation you take. So if you take, means if you take these two set, self set, and these two sets are the set of the boys of a class 11th 12th science, whatever. So if you take any two students from here, if you subtract their height, are you definitely going to get less than 3 meter? Obviously, it's definite. So I hope these two relations clear. I have explained in a very, very simple language. If you still got, just confirm from me, and just let me know that, so that I can clarify in more better way. Now let us proceed to the next type of relation, that is reflexive relations. That is one of the most interesting relation. Here comes the next relation. It is a very nice relation. Reflexive, reflect. The name indicates reflect. So a relation R in a set A is called reflexive if A comma A, mind it, A comma A belong to relation. For every A belong to the capital A. So let me understand. I hope it is clear. Now listen. So let us consider that there is a set A. It's one set. So it has one more. Let us take another set of codomain, and there is also a set A. Means they are consisting the same type of elements, because already it is said here that a relation R in a set A, that means A cross A. So let us consider the following elements are present in the set 1, 2, 3, 4. Here also similarly 1, 2, 3, 4. When a set, when a relation will be reflexive, when A comma A means the same element is double up in an ordered pair. Suppose if I consider 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4, and it is the example of a reflexive relation, because here all A comma A belong to R is present, and remember there is a condition for every A belong to A, means all the numbers should be included, then only it is a perfect and eligible relation, fall under the category of reflexive relation. I hope Takuaman it is clear to you. So listen, so if I hit a question here, can I say 1 comma 1, 2 comma 2, 3 comma 3 is a reflexive relation in this question? Does the definition satisfy the example? What do you say? Can you say this example is a perfect reflexive relation? What do you say, Chinmoy? No, because there is a condition for every A belong to A, means for every element of A should be present there. But there is one thing is missing, that is what? 4 comma 4 is missing. So we cannot consider, in absence of one element, it is not a reflexive relation. Let me arrange one more case in this matter. Can you say that is a reflexive relation or not? So if I mention this 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4, and suppose 1 comma 2, there is one extra unnecessary element is present or ordered pair is present. Can you say this is a reflexive relation? What do you say? Taimangha, what do you say? Yeah, this is also a reflexive relation. Though we have an extra ordered pair here, or the extra element, we don't mind for that. We do not consider that the presence of extra element, though the definition satisfies or not. we have to only focus on the definition satisfaction or not. Yeah, in here all the a comma a, for all a belong to a are present. 1 1 2 2 3 3 4 4 are present. Yeah, it is an extra element present or the extra order presence. We didn't bother about it. It is also a reflexive relation. I hope you can gauge what I like to convey through this. I don't feel that you are feeling comfortable through the okay, leave it. It's great. Now I can change the formulas also, means I can change by the example also. It's your wish. Suppose by the example, suppose let us consider a as PQR. So the set a is a PQR, then this one more set PQR. If I ask you, draw the or write example of a reflexive relation. How to write? Same P Q R. That means what? Same elements of the particular set is repeated. I hope it is crystal clear. So let us jump to the next relation, that is this transitive relation. Now here goes the next relation, that is your example of symmetric relation. Symmetric relation. Symmetric relation. So what are symmetric relations? A relation R in a set A is called symmetric if A1, A2 belong to R. Also implies that A2, A1 also belong to R, means R means relation for all A1, A2 belong to A. So what does it refer? Let me make you understand it. So what happened? The reverse is also present in the same relation. It's called your symmetric relation. Suppose consider a relation set A and the elements are 1, 2, 3, 4 and this one other set 1, 2, 3, 4. If I say here as a relation, if I say 1, 2 is an element of the relation R is equal to 1, 2, then definitely there should be 2, 1. The reverse order of the same order pair should be present. If this reverse order is not present, we cannot consider it as a symmetric relation. I hope it is clear. Means 1, 2 and 2, 1 should be present. Means A1, A2 is belong to R. Similarly, there should be A2, A1 also belong to R should be present. If it is satisfying, then you can clearly say that it is a symmetric relations. I hope it is clear. Yeah, it's good. So let me give you some more example to make you understand much better. So there is an example given. Suppose consider 1, 3, 1, 1, 2, 3, 2, 2, 3, 1, 3, 2. Is this a symmetric relation? What do you say? Definitely. Why so? Because you can see the reverse order is also present in this relation. If I say 1, 3, that means there should be 3, 1. Yes, it is present. Okay, it's validating. 1, 1. It is what? 1, 1. What is the reverse of that? 1, 1 only. So already is there. Self-existent, the self factor of this. 2, 3. Let us see whether reverse is present. Yeah, 3, 2 is also present. Yeah, it is also validating. 2, 2. It is really identity or it's a reflexive. So what you can say, this is a perfect example of a symmetric relations. I hope you can gauge what I mean to say. Okay, so this is what I am saying. Suppose let me give one more example. 1, 1, 2, 2, 3, 3, 4, 4. Is this a symmetric relation? Yeah, definitely. It is symmetric relation as well as the reflective relation. It's satisfying both the definition. So this is a good example of both symmetric. It is symmetric also and reflexive also. All right. So you cannot say that every time the reflexive can be a symmetric. So point to be noted. Sometimes in some special cases we can clearly say that the relation is a symmetric as well as reflexive. The condition are such like. You can also expand the relation. Suppose let me make it more broad so you can understand better. So if I use 1, 2, 3, now what can you say about its function? Means what relation? Is this is still a symmetric relation? Not at all, my dear. It is not a symmetric relation still, because 2, 3 is present and there is no any reverse order pair is present. Though it is reflexive, but it is not a symmetric. To make it symmetric, there should be an ordered pair. There should be a reverse order of this element should be present. That means 3, 2 should be present. In the absence of these 3, 2, we cannot say that this is a perfect example of a symmetric relation. I hope you can catch the concept. There is still many things. The video will become very lengthy if I go on explaining each and every depth of the concept. I hope you can catch what I mean to say. Just write it down. So here comes the next relation. That is what? Transitive relation. What does it actually indicates? Let me make you understand. A relation R in a set A is called transitive if A1, A2 belong to R and A2, A3 belong to R. Also implies that this A1 and A3 is also belong to the relation, such that for all A1, A2, A3 are all belong to the set A. For example, let me clear it up. Suppose a set or a relation consists of 1, 2 and then 2, 3 means A1, A2, A2, A3. If there is A1 and A3 is also present, A1 and A3, that means what? 1, 3 is also present in that relation, then that relation is a clear cut a transitive relation. I hope it is clear. 1, 2, 2, 3, 1, 3. What does that mean? If 1, 2 is present, 2, 3 is present, there must be or there must have to be 1 and 3. 1 and 3 should be present. Then it is a satisfied transitive relation. I hope you got it. A, B, B, C, A, C. Through the alphabetical order. If I use alphabet, how can I say? If A, B is present in the relation, B, C is also present, then there have to be A, C is also the element present in that relation. Then it is a transitive relation. I hope you can catch what I mean to say. So now a last concept that I like to mention here, that is your equivalence relation. Equivalence relation. You might be thinking, what is this? I have not mentioned it earlier. Very simple. Remember, if any relation satisfying reflexive relation, transitive relation, as well as symmetric relation. What I mean to say that if a relation is symmetric, reflexive, transitive, means it is 3, then it is called a equivalent relation. I hope you got the definition what I mean to say. Means if a relation is transitive, reflexive and symmetric, then it is called a reflexive relation. So nice, so easy, isn't it? So what you can write, if is I hope you got it what I mean to say. So now if you really have understood the concept, then you can carry out with the exercise. The exercise 1.1, the very beginning exercise of your class 12 science. So most welcome. So stay tuned. I feel really happy that you are very interested and I got your concern. I was waiting for the day. Thank you. Alright, so in the upcoming sessions, in the next video, I like to proceed the exercise. I want you to follow it and clear it, the concept and definition what I have discussed here, so that we can very nicely do the exercises. And if you can carry out with the exercise also, and please send me my WhatsApp number. You know my student what I means. That's fine. Thank you.